And it's a pleasure to have Dragomir Saric from New York and now in the IS, who will tell us when the geodesic flow is ergodic.
Oh, thank you very much. That's an excellent question. It's my joke. Okay. Now we know when to laugh. All right, so it's a pleasure to be here. So I'll start by setting up things. So X is an infinite surface, infinite Riemann surface. H is maybe upper half plane, and gamma is the Fuchsian group provided. Infinite means the Fuchsian group gamma is not finitely generated. So here's a theorem, which is known as Hopf, Suji, Solomon dichotomy or statement. So the following are equivalent. First, geodesic flow on the unit tangent bundle of X is ergodic. Second, Poincaré series for gamma is divergent. Third, Brownian motion. So, second?
Poincaré series divergent at
one.
At one.
At one. So that's some e to the minus hyperbolic distance between point Z and the point in its orbit is infinite. Gamma in gamma.
These lights, they're flicking. Right? Maybe I'm getting mad.
All right. So the third property is Brownian motion. Okay, now I'm confusing my spelling. Brownian motion on X is recurrent. Then number 4, the X has no Green's function. So a nice notation is X is the element of the class null G. No Green's function. G is for Green's function. And number 5, which I will be using a lot, is that modulus, and I'll explain what that thing is. Modulus of curve family connecting a compact subsurface of X to its ideal boundary is 0. And by curve family, I mean all curves connecting a compact subsurface going to infinity, basically. The modulus is 0.
So you said now that gamma is not finitely generated, right?
Gamma is not finitely generated.
But this theorem holds also the finitely generated?
This is all true if finitely generated without, I mean, it's true. But this is equivalent in infinitely generated, right? So some surfaces are in here, some surfaces are not. So I'm interested in surfaces which are in here. And all these properties hold for all of them. But some of them are not here in this class. So those are equivalences. Not every surface which is infinitely generated is in here, right? But if surface satisfies one of the properties, then satisfies all. Yeah.
What's modulus?
So I will explain now. I'll give definition of it.
Okay, and the Green function as well.
Green function is a harmonic function which has a logarithmic singularity at one point, and it goes to 0 on the boundary. So it's analog, like if you look at random walks and things like that. That's all. Okay. All right, maybe I should do here. Light is not good here, right?
So ergodic here means since it measures infinite, that
Measure is infinite. So little measure is infinite, but the invariant set
is out there.
the invariant set has 0 measure, or the complement of the invariant set has 0 measure. Okay. So what is a modulus? So here's the definition. So if you have curve family, let's say C. So curve family is uncountable self-intersections intersecting each other and so forth. So it's a very general statement. So then we can talk about conformal metric. So we are somewhere on the Riemann surface, so the notion of conformal. So conformal metric. So it's non-zero, non-negative, and Borel measurable. And we will say that this metric is allowable for C. So the metric is allowable for C if the length of every curve in the curve family C with respect to this metric, that's just a gamma. Rho of Z, absolute value V Z is greater or equal than 1. So we normalize this metric among all the metrics, we normalize them by this condition. So that's what allowable means for the curve family. And then modulus of the curve family is infimum of the row area of your Riemann surface. Infimum is all row allowable. So you consider only allowable row, and if something is not allowable, as long as this infimum over this is positive, you can scale it to be allowable, and you look at the row. So that's conformal invariant and quasi-conformal quasi-invariant. So examples. Examples. So if you take a square, rectangle of sides A and B, and if your curve family consists of all curves which connect top to bottom, all of them, then the modulus of this curve family is AB over B squared, which is A over B. So basically, among all these allowable metrics, the one which is given to you by Euclidean metric divided with B is the one which gives you this infimum. So this metric is extremal. And actually, this is called Dragomir argument, and that was the beginning of quasi-conformal maps. All right. And you can also notice that instead of taking the full family of the curves, you can only take vertical family of curves, and that also has the same modulus. Somehow same. In this case, yes. Not all.
That's related to the capacity, I guess.
Yes. Another example is annulus, Euclidean annulus, and here I choose to consider curves which connect two boundaries and say this one is has radii R1 and R2. And then what you can do is you can cut your annulus by a straight line and you map it with logarithmic coordinates. And my logarithm, right? So make some logarithmic coordinates here, log z. And then your curve family becomes curve family which connects these two vertical sides, and you can compute that just by using this one. that the modulus in this case is 2 pi log R2 over R1. And notice that if R1 is 0, then you are actually connecting boundary to a single point. And in that case, a modulus of this curve family is 0. So modulus of the curve family connecting some complex set to a point in the complex plane or Riemann surface, the modulus is 0. So notice here, modulus 0. So we are asking somehow in some way a question, what is this point at? What is infinity of Riemann surface looks like? Is it like a point or it's more a point? So that's kind of intuition here. Okay. So my interest in this theorem was actually sort of connections with hyperbolic geometry. Actually, there are like maybe, I think I was able to count 30 different conditions which are equivalent to this one. So this is kind of very nice thing. But I couldn't find anything that uses hyperbolic geometry beyond the Poincaré series, but that's kind of hard to kind of see. You have to count something about the orbits, that's hard to see. So instead, I wanted to do the following. I want to look at my infinite surface. Here is one example.
I guess the limit set, must be, what's the story about that? The Poincaré series is related to the limit set.
Yeah, so
So to be ergodic, you have to have
the conical limit set is measure 0. Something like that. So there are other things. So sort of, if you look at surface like this, then you can break it into pairs of pans, and you can make these pairs of pans to the boundary geodesics to be boundary curves to be hyperbolic geodesics. And so once you do that, then every pair of pans is completely determined by the length of the boundaries. But what else you need to determine the surface is how these pans are glued along the boundary geodesics. From now on, boundary geodesics I will call cuffs, just for short. Yes.
If you're making a Riemann surface of infinite type.
Yes. So this continues. So you have the lengths, and then also you can draw unique orthogeodesics between two cups. So you have it from one side.
Straight. You defining a class of set surfaces.
So I'm first saying how can you construct a Riemann surface from the hyperbolic geometry, and then I'm going to ask whether it's in this class or not.
These particular examples, or that's the most general example?
Oh, this is a general example.
Okay.
All right. So basically, once you set up topology and path decomposition, then you can read off the geometry from this data, right? So the data are the lengths of these cuffs plus how you glue, which you measure as the distance between the foots of these orthogeodesics. So you have, if the set of cuffs is alpha n, then you can talk about lengths of alpha n's, and you can talk about these offsets here, which are called the twists. So for each cuff, you have these two numbers, and you take the set of all these numbers, and these are called Fenchel-Nielsen coordinates or parameters.
In terms of, if I start off with every Riemann surface is realizable this way.
Yes.
And what's the condition on the length and twist? Anything?
There are no conditions. Everything is free. So I'm asking is what conditions I need to
a complete set of. I mean,
to be complete? Yeah, then there are conditions. It's not solvable in general, but I'll give you some sufficient and necessary conditions that you will see. But basically, I want to think about all the surfaces which are given with this data. And I want to ask, so this is like, for me, very nice picture. You can see how to build a surface. And I want to ask, when is this surface in this class? When is geodesic flow ergodic, which is equivalent to all other things? So that's my question. So the twist, I will use a relative twist. So there'll be in the interval -1/2, 1/2. So I take the offset and divide by the length of the curve. And then there's some choice of orientation. So this would be maybe positive twist if it's like this. And if I want a negative twist, then I would glue them in this way. So this twist here would be negative. So this surface has one end, and it is accumulated by genus. It's called Loch Ness Monster. All right. So that's the question. You are given topology, you are given path decomposition and a bunch of numbers, and the question is, what does sufficient or necessary condition for these numbers to give you surface in the class given there? So that's the type of things I like to think about. Right. Another nice surface is the infinite fluid surface. So here, this is infinitely long, and this is a puncture. So it has infinite length, but finite hyperbolic area. So conformally, these points, the neighborhood of these points are disk minus a side. And then in this case, when you take path decomposition, what you see is the first pairs of paths has one cuff and two punctures, and then the second pair of paths has two cuffs and one punctures, and so on. So this surface is essentially in this class, even though each puncture is like an end of a surface, it's a simple end. It has this kind of simple topology. But there's one infinite end which is accumulated by all these punctures, and that end is accumulated by genus. But kind of looks the same. Sort of my question that I'm interested in here is actually breaks. So the types of conditions I'm getting, it breaks the family of the surfaces into two classes. One class is surfaces which have uncountable many topological ends. And that's a complement of a Cantor set in a Riemann sphere and things like that. And another class is surfaces which have finitely many ends or countable many. So today I'm going to talk about results for finitely many or countable many ends. I'm not going to go and talk about that the other one. So my surface has finitely many ends, and that's the main case, basically. Okay. So what do we do here? Well, according to this criteria, we consider a compact surface or finite area surface, subsurface, and we connect it to infinity by all possible curves, and we want to find the modulus of this curve family. All right, so okay, so see all curves connecting.
So suppose I take, as you said, the Riemann sphere, and I take open set.
Okay.
I don't know. I mean,
Then your surface, yeah, so your surface doesn't have a geodesic flow record
why is that?
because it has a big boundary, so the geodesic flow can escape. The geodesic can escape, so there's no risk. Or you can make a Green's function easily.
Okay, so I think that's why I was confused. And you said that this is all obvious in the geometrically finite case, yeah. The minute there's a free boundary, it's all over.
Yeah, that's right. So when I said geometrically
that's why I was asking you, Sullivan always considers the convergence and with the induced measure, you know, when he does the rigidity relative to the limit set.
yes.
But here you're just asking, and in that case, you need to know the conformal dimension and whether the thing converges.
Yeah,
that's
the
dimension.
Yeah, that's the
looking.
Yeah,
okay.
That's the
You're not
conformal.
looking at this renormalized.
No. But that's a
whatever
different question.
measure.
Yeah. That's Patterson-Sullivan measure. So, yeah. That's a different.
So you can ask relative to the Patterson-Sullivan measure when it's
You can ask
when that
some of them convergence of Poincaré series and
All right. Now I understand.
And Green's
Really
function,
just
maybe.
this boundary where the limit set is everything.
yeah. So but I'm trying to kind of get to the like some techniques here or something. Sort of like so we look at all curves connecting set K to infinity. K to infinity of the Riemann surface X. And first,
Sorry, K was your first layer there?
K is first surface, yeah, this K. First surface. First pair of paths.
Yeah.
So the first idea is that, okay, so let's look at the polar neighborhoods of this simple closed geodesics, right? So you have this polar neighborhood here, you have this polar neighborhood here. We know that they are disjoint, and we have estimates on their width, right? So if you have so if alpha is a simple closed geodesic, then you can define the polar neighborhood of alpha to be all the points z in your Riemann surface X, such that the distance from z to alpha is a constant, which is a function of length of alpha. Sinch inverse.
Hyperbolic then?
Yeah, hyperbolic metric. So yeah, this is all hyperbolic metric. Like I'm building surface using hyperbolic lengths. So sinh inverse 1 over sinh length of the curve alpha over 2. So if you choose this distance, then you get the colors which are disjoint. If the curves are disjoint, you get colors which are disjoint. So that's kind of precisely computed. And then we can talk about extremal length of the curve family C, and that's nothing else but 1 over the modulus of C. So take the direct reciprocal of that, and then this condition becomes when is the extremal length infinite instead of modulus being 0. But this is convenient because this extremal length, since you talk about extremal length, you talk about length of the curve family in some extremal sense, but then since you connect this curve family to infinity, you connect two sets. You can start saying extremal distance, extremal length, you can talk about extremal distance. So this statement can be rephrased that extremal distance to boundary of X is infinite.
You mentioned the name of somebody who introduced this skills. I thought that there was a big fight between Alfors and Berling. They're falling out.
I don't know that. I know
The
that.
definition of extremal length.
You
don't?
No, I know.
Yeah, as to who invented it. So
Well, they always say Berling invented it, but Alfors developed it together with him. That's what they say. So
who's the name you mentioned? You said the first person to edit.
Did I say something?
Yeah, you said a name up top there with computing the.
This thing, oh, this is Gretsch argument. I don't know. I don't know what that's spelled.
And you said he invented quasi.
He invented this method. He proved that this is extremal metric, and that was the start of quasi-conformal. He didn't call it quasi-conformal. Some other people. Let me not go there. But anyways, so going back to this problem. So now we think about whether the extremal distance from this boundary to infinity is infinite or finite. If it's infinite, then your geodesic flow is ergodic because you can never reach infinity, right? If distance is infinite, right? Sort of that's kind of intuition. But the nice point about this terminology is that agrees with what you would think about distance between sets. So basically, if you define Cn to be intersection of this curve family C with colors around alpha n. So those are so you have these curves which go around, but then you have a sub curves which stay here. So you break each curve into sub curves C1, C2, C3, and Cn. So then the extremal distance of the curve family C is greater or equal than the sum of the extremal lengths of Cn. So somehow going from here to here, that length is bigger than line going from here to here, here to here, some of these lengths. So that kind of conforms to that kind of regular notion. And then, okay. And then what's the point of all this? Well, the point of all this is that we can estimate what is extremal length in an annulus. Color is like an annulus. We can estimate that. One way of doing it is, let's say, okay, let me take one color, right? And take its universal covering, make curve alpha to be the, say, y-axis. And then you will have two geodesic here orthogonal to curve alpha. And this is the length of alpha. So this is L of alpha. And then when you add this by the element, by the element which glues this one to this one, you go back to your annulus, to your color, right? And then what you do is you say, okay, let me take log z coordinates again, and I will get, now this will be mapped into a rectangle, and I know what to do there. So the length of alpha is this side, and this is angle. If this angle here is theta, this is 2 theta.
Theta comes in this picture.
Theta is this angle. So theta is determined by the width of the column. Like the bigger the width, the theta is bigger and going to pi over 2. Right, so this thing here, if I call this number W of alpha, then this length here is W of alpha. And this theta is actually functional W. So it's a simple fact in hyperbolic geometry. But so we are given this is given, and then
given a list of lengths and twist, but for the moment you ignore the twist.
For a moment I ignore twist, I just look at one cuff, alpha, and I want to estimate the extremal distance between the boundaries of this color.
And the size of the color does not care about the size of the
other colors.
Alpha, it just
that's the point. So they are disjoint.
This way, they're going to be disjoint automatically.
Yeah, that's the color lemma.
I mean, this is to apply your lower bound. So
to apply the lower bound. So I want to estimate this thing one at a time. So this is like very kind of first thing that you would try. And then you have this width of the color that gives you the angle theta, and then you hit it with logarithm, you get this thing, and then you're basically estimating modulus of this curve family 1 over the modulus, and you can see that the modulus of this curve family C alpha, let's say this is alpha n, Cn is actually in these coordinates is essentially the length of alpha n times 2 theta, that's the area, divided by normalization, which is the minimal length of this one, which is 2 theta. This is 2 theta squared. So you get length of alpha n times theta times some constant over theta times a constant like 2. And then it just happens that this theta is very small when alpha is very big. You have very shrinked
How
color.
do we see theta in this picture of this?
This is theta.
Let's go.
The angle.
Angle between this boundary of the color and the geodesic in the universal color.
Just computing it in this.
So this is the geodesic, and here is boundary of our color on one side. So this one is here. Okay. So and then if you know a little bit of trigonometry here, then you know that this is actually length of alpha n times e to the length of alpha m over 2. You get asymptotically, not equal, but asymptotically when length of alpha n is very big. Okay, so that's kind of a simple-minded computation. So you get that x with parameters L of alpha n and T of alpha n is in this class O sub G, a good class that I like with all these properties. If sum n goes from 1 to infinity of here you get 1 over the length of alpha n e to the minus length of alpha n over 2 is infinite. So that's a very kind of simple condition that you can get here. So, however, when we look at this thing, we're not quite happy with that. And I can tell you the reason why we're not happy. So let me just call, So we're looking at this surface, right? And as you mentioned, we didn't use any twist, which is fine. But we know very simple surface of this type. That's a surface when all the twists are 0. Okay, so when you start drawing that surface with some length, so you have all these pairs of pans, and twist being 0 really means that when you take orthogonal here, there is a single unique orthogeodesic here. If the twists are 0, then the next orthogeodesic between these two meets this one here, exactly this point. That's a twist 0. They just exactly match. There's no offset. And then you keep going like this, and it's always like that. And then we knew, since they all are kind of, so this is length L1, L2, L3, L4, and so on. Since they all continue in a sequence, we knew how to compute this length. Just add them, right? And this length, let's call it d infinity, turns out to be asymptotically e to the minus ln over 2. So we get similar to this thing without 1 over ln. That's what we get. And if this length is infinite, then my surface is complete, which means that when you take union of these pairs of pans, it's a complete metric space. Another way of saying that is the Fuchsian group is of the first kind. So this infinite is equivalent to saying that X is complete as a metric space, as you're measuring, right? There's no openings. And that's equivalent to say that gamma is of the first kind. Okay, so when you look at this situation, we have a sufficient condition for being, for geodesic flow being ergodic, which is this condition here. We have a sufficient and necessary condition for being of the first kind, focusing group building on the first kind, of X being complete, but we don't have a complete picture. So there's a gap. And gap is what happens. What happens if this 1 over the length e to the minus length over 2 is finite? I'm saying that's right. But this other this is finite, but this other length is infinite. So far, what I tell you, I would consider trivial. So that was a actual real question. Okay, so we have this simple computation, and we have a gap even for the twist zero. So then we had a sort of idea, which I want to maybe put here. I get the feeling that the first board you can see the best. So how to deal with these things? So you see when you look at this one pair of pants, and our color neighborhood, or half of it is here. There's another half on the other side. So then, well, if you take orthogonal geodesic, you will hit from the puncture, you'll hit here exactly at this point, and it will go back around in the same way. So there is this color, which we now call standard color, and we notice that there is a space here. And my picture is not doing justice. This is very tiny. It's very very tiny. It's hard to draw. But it's very tiny space, which is kind of X. So if you look at this picture here, you can keep adding this extra space in between and making these colors bigger. So this one we call non-standard color. So this kind of way of adding. And our first result is that the modulus of non-standard color for the curve alpha is actually asymptotically equal to the length of negative length of alpha over 2. Oh no, sorry, length of alpha over 2. So that's a joint result with Ara Basmajian.
This is a local statement.
It's a local statement. And Hrant Hakobyan. And that was the beginning of something in Montreal. It's very interesting.
So, Finnish.
Sorry?
That fellow Finnish.
Hakobyan? No, he is Armenian. Both are Armenian. Well, this guy is New Yorker.
Guys are Finnish.
This guy is New Yorker.
Okay.
And this guy, he was student of Chris Bishop. Yeah. When I was a postdoc at Stony Brook, he took my class. So it is. So anyway, so I should maybe point out that computing this modulus is almost impossible unless you are in some very nice cases, like symmetric cases. So this is an estimate. So what we accomplished here is we gave like asymptotically correct estimate when the lengths are going to infinity. So
I mean, how do you do that?
how do you do that?
Understanding words.
Yeah, well, here's the picture. Let me draw a picture and just a few words.
You're really estimating the capacity.
Really estimating this. So so this is our cuff alpha. So let this be alpha tilde. So this is this side of the standard color. So this this boundary, which is not a geodesic, it's a hypercircle, is this line here, right? And then you have this geodesic, which is tangent. So you have thing here, and then another lift of the same geodesic is here. And then you draw orthogonal at this point. So that is this one here. These two are orthogonal. And there is another orthogonal here, I guess. It's the lift of the same one. So then the standard color was this. Half of the standard color was this. And then this is this sliver. Okay. And then again, we map it with log z. And we see a picture like this. This is the standard color. This is standard color. And then here we see extra thing that we added. And you want to compute modulus of the curve family going from here to here. We have an explicit function, but that's not usually very useful in estimating modulus. So what we were able to show, and I think I'm kind of running out of time, so I won't be able to show you a plan, but what we were able to show is that essentially, asymptotically, you can estimate modulus of this thing with the integral of the height function. So you basically integrate the height function, and that's the estimate. And the reason for that is, maybe I can erase. The reason for that was that you can kind of start introducing a good metric for this curve family, and that's the one where you fix delta, some small but positive number. And everywhere on this line, if this is x, you draw in rectangle of width delta, and everywhere on this line, including the one below, you make the metric to be Euclidean metric times 1 over the height of the rectangle. And you kind of see somehow that when delta goes to 0, you are seeing limit of a Riemann sum for that integral. So that was the idea. Kind of approximated, then you have to show that it's asymptotic, there's some work. So this is not quite easy, actually. When I was looking at this thing, I was searching all these, as you said, Finnish papers, but I couldn't find anything, so I have to do it myself. And I did it by hand, actually, because my mathematical license expired. I had to wait for 2 weeks, so I just did it. That was just before AI, so I couldn't use it. Anyways, so you get this bound. So then we have a theorem which sets Basmajian, Hakobyan, and myself. So we get theorem. So we have x. So x is the fluid surface with lengths ln and twists tn. So this is parabolic, or no, that is in, well, let's wait. Element of this nice class if sum n goes from 1 to infinity e to the minus ln over 2 is infinite.
For any twist.
No twists,
Oh, this is the
without twists.
that
So Tn is 0.
Tn is 0.
Any Tn. Any Tn. So in particular, when Tn is 0, this gives you complete quantization. So if Tn
And Tn,
if Tn is 0, then that fills this gap. If Tn is 0, then X is in this class if and only if X is complete, if and only if this sum is infinite. That's complete quantization only in the twist 0. And this is sufficient condition when you don't know anything about twists. Okay. So that's what you get. All right. And again, you're not happy. And as you said, we're at a twist. So that's why you're not happy. So you want to figure out whether twists can help. So we have another version where, so I'm trying to draw, this is going to be very hard to draw. Let's say, yeah. So here is the next pair of pants, the twist is not 0. So then again, we can talk about the standard, other half of the standard color, or we can add, this is the standard color, and this is this geodesic which goes to the puncture. And then again, we can add this thing, so we add on both sides, we add these slivers. Then we have the result, also same authors. So if sum n goes from 1 to infinity, e to the minus 1/2, 1 minus absolute value of the twist times ln is equal to infinity, then the geodesic flow is ergodic. So we were a little bit happier with that. So we should immediately compare, for example, here, if you choose ln to be 2 log n, that works because you get 1 over n, and we know that diverges. Here, we get a bit more because we can multiply this constant with something smaller than 1. So for example, if you take all twists to be 1/2, exactly 1/2, every time you do 1/2. So that's the sort of maximal. That's kind of a nice picture. So here, let's take 1/2. Then this condition becomes sum e to the minus ln over 4. So which can be compared to this on minus ln over 2 being infinite. And for example, ln equals 4 log n works. We were quite excited about that. This also works in not only in this case, but it works when you have this same sufficient conditions work when you look at this Loch Ness monster.
Let me just understand that the pimple at the top is the same everywhere. No, it's
This
a
one-
Loch Ness monster.
No, they're not. They're also, it's hard to draw.
What are they? Don't they have
Yeah,
parameters?
they have some lengths.
They are pairs of whatever.
There is a pair of paths. Yeah.
They are one punctured torus with a boundary.
Yes. One function source with boundary. But you can put even more.
But don't they have parameters also?
They do. But they're not so important.
Don't enter into this.
They will not enter. So the condition for the Loch Ness monster, if you have these lengths, which are cutting off the infinity, and if you have these lengths, which are cutting off the extra thing, so the only condition, in addition to this, that you need to impose is that these cutoffs are bounded from above. So if you have
Modular space you don't have.
sorry again?
In the modular space of one punctured tori, you're not near the boundary.
Yeah. But here, like if you squeeze this to a puncture, then you're here. You just kind of,
So that's
so that's kind of, so if you have this thing, and again, this sum e to the minus 1/2, 1 minus absolute value Tn, Ln being infinite, then X is in this class. So those are kind of the results that we had. And we were kind of expecting that that's the sort of close enough to being complete description beyond sort of beyond some level of the increase of the length. We were expecting that that the surface will not have a geodesic flow ergodic. That is reasonable because you kind of have these lengths, and if they become really big, then you expect that geodesic flow can just escape. That was our expectation. No matter what the twists were, that was our expectation. So we talked about people, and then there was a conjecture by Jeremy Kahn and Vlad Markovic. So they said for any ln, there exists Tn in minus 1/2 such that this surface with these parameters, Ln and Tn.
I want to take you back for a second.
Sure.
That equivalence.
Yeah.
The one about recurrent with Brownian motion.
Yeah.
Terry Lyons have a theorem about when that's recurrent and what's that in what terms? Do you know what I'm talking about?
He had a theorem. The most famous one about this stuff that I know is that that there are surfaces where
I mean, I'm just talking about the recurrence, which is probably what a lot of.
well, this is before him.
So I vaguely remember him having a characterization of the ones which are recurrent.
He had
You have a Riemann surface, you ask when is Brownian motion recurrent. It's a very natural.
but characterization in terms of what? In terms of one of these.
Yeah, I don't know. That's maybe you just proved one of these equivalences.
Yeah.
I don't know.
Yeah.
You don't know.
I don't know. I think that these equivalences are certainly before him.
Yeah, I just
He
remember.
had something about
I remember Sullivan being very excited by what he.
Yeah, so that was about existence of positive harmonic functions, not about Green's function. I can talk to you about that later. But anyway, so here, their conjecture is that no matter which lengths you take, if you choose the twist appropriately, you can make the surface have a ergodic geodesic flow.
Say that again.
About completeness.
If it's geodesic flow is ergodic, then it's complete.
No, but is it easier to show that the surface is complete or?
Yes and no. Depends on the. I can tell you. I had a very ambitious plan, but I can tell you all about that. Maybe if you go to the university.
But Repeat the conjecture.
So the question is, can you characterize when the surfaces are complete in terms of the twist? So if they are in this class, then they are complete.
What do you mean by complete now?
It means that the Fuchsian group is of the first kind, that the union of these pairs of bands is the complete metric space. So you can have weird things where okay. All right. Let me draw a picture for that. So you can have a weird situation where these lengths increase very rapidly and then they accumulate to actual open geodesic. And then to complete it, you have to add half plane. It's weird, but yeah. If you're interested in that, I can tell you more, maybe.
Sorry, I've forgotten what we said. What does first kind mean? Limit set?
First kind limit set is everything. Second kind, so this
Okay,
is the second kind. So what happens is that for the limit set of this Fuchsian group, you have an interval.
So you're going to have a free edge.
But no, you don't have a funnel.
Yeah.
You don't have a funnel. You have
It's not geometrically fine.
yeah. Anyways, but for us, this was a big conjecture because we thought that if the lengths increase too fast, this can never be true. That all of the surfaces are either not complete, or maybe if they're complete, well, at least they're not geodesic flow is not ergodic. And they did this conjecture. We kind of don't know whether to believe them or not. They had a good reason to give this conjecture because they just proved this surface subgroup conjecture, and there they use the thing which called offset, and for us we call them twists. And they use this twist to show some. They use it for compact surfaces, but their compact surface had large genus, so did a lot of twists, and the lengths were big, and they proved the theorem. Like main step in the proof was that. So they had a reason to believe that to be true. So on this we have a sort of partial result, which I think it's also interesting. And since I'm running out of time, maybe I can just state that result. So this is a new theorem. It's due to Hakobyan, Michael Pandazis, and myself. So we said the following. Okay, so somebody gives you twist, for example, n factorial, not twist, the lengths, n factorial. Can you choose the lengths such that the surface is not only complete, but can you choose the twist such that the surface is not only complete, but the geodesic flow is recorded? So that's basically what they said. It should be possible. So we have the following. So for any choice of numbers, positive numbers, and there exists a choice of some numbers ln, which are maybe even bigger than these AMs, such that the fluid surface X, whose Fenchel-Nielsen parameters are these bigger numbers ln, and twists are always 1/2. So I always choose the 1/2. So it's like here, right? Always 1/2, but the lengths are really big. This surface has ergodic geodesic. So we did not quite prove the conjecture. We had to
proving it with 1/2, but you have to increase the
lengths. Yes, lengths have to be increased, but in spirit they are right. I don't know whether they really mean precisely this. At least that's how we kind of after talking to them, and it's kind of just we talked to them separately, and both of them said the same thing. And we kind of, okay, this is the conjecture, and then we said no reason to believe, and then based on these things, I was hoping it's not true, and then so I asked my student Michael to disprove it for 1/2 twist, and actually it turned out it's correct if you increase the length. So the reason why we thought it's not true by 1/2 twist because we have this previous theorem. So that's Basmajian, Hakobyan, and myself. We said if ln concave lengths, then x is in this class being geodesic ergodic, if and only if concave lengths and twists 1/2. If and only if this sum e to the minus ln over 4 is infinite. So somehow we were able to say for the half twist, which is the most symmetric case, so half twists, they have front to back symmetry, right? Because each pair of pants is actually pentagon with 1 0 angle and 4 right angles, and there's the same one on the other side. There's front to back symmetry. So we thought that we should at least be able to characterize things for the half twist, and we add the word concave. We had to add the word concave. So we add the word concave, and we prove that's a characterization which says that lengths cannot be super exponential or whatever. And also we kind of thought, well, at least 1/2 their conjecture is not true, but after doing some work, we showed it actually is true.
How does concave come into the picture?
It's a condition when we are doing some summation, it pops up. We don't have a reasonable geometric explanation for that.
When they make that conjecture, exists Tn, I mean, would the random guy try to do it? What happens if you chose to?
Oh, there's another work in progress. We're trying to say what happens in random. We're trying to say our conjecture is you cannot go super exponentially through randomly. So we have to say that this is very, very
real. I understand when they make that conjecture, what are they thinking of?
And there's a choice.
Yeah, and why that choice is trying to do what?
Trying to make the geodesic flow ergodic. So they were saying like
they're trying to help kick it
back. Yeah, that's what they were saying. Like when you look and then if you follow geodesic and then if you do a good twist, the geodesic come back.
So that's why I'm asking what you know what happens if you choose this is random.
We have some work in progress. We know that randomly, if the length is n log n or less, randomly, every such surface is complete. And if it's n log n to some power bigger than 1, where log n is to the power bigger than 1, almost every surface is incomplete. But we don't know what's the story for ergodicity randomly yet. So it should be in this between 2 log n and n log n should be somewhere cut off, and we don't know yet. I hope.
The random probably kicks it back, right?
Random kicks it back, yeah. But I'm talking about the random choice of twist, right? So randomly you choose a twist. Random choice of twists.
Yeah. So what I'm saying is maybe in their conjecture, it's not their exist, but maybe the random. Is that possible?
No. So what I said, this is not yet available, but if the lengths are at least n log n to the power r, where r is bigger than 1, then randomly your surface is incomplete.
And they still believe there's a choice.
Well, they didn't know that. This is coming after this. No, they only knew this results when they made. They only knew this condition when they made their conjecture, and I didn't believe them. And I tried to prove, at least for 1/2, that that's not the case, and then it turns out it is. And now I'm trying to say what happens when the lengths not too bad. So in this case, they are incomplete, so they cannot be ergodic, almost surely. And if you are, in this case, then almost surely complete. But I don't know, like in between here, maybe there's a nice cutoff, maybe not. I don't know. Okay, so I'll stop here. Thank you.
So, in none of these conditions that you wrote at the beginning, did Fenchel the FN parameters appear? So is that part of the appeal of these theorems that it's?
Yeah, it's my appeal is that I like to draw these pictures and I can understand them. It's kind of elementary, and then you start asking questions based in this analog, right? There are no Fenchel-Nielsen, and I cannot hope to have complete parameters, complete answer in terms of Fenchel-Nielsen coordinates. That's too much. But I hope to have a good picture. Yeah.
And so, were there any nice sufficient conditions in terms of the FN parameters known before this? Or?
No. Okay. No. This is like I just started. So we started with these silly standard colors, and from there we started building. So I was able to add one more condition here, but that was in terms of holomorphic quadratic differentials. So they're not in terms of cogeometry. Yes.
So when these Poincaré series converge, do you have any idea like what are their values?
No.
Oh, okay.
No.
Like what kind of numbers are they?
No idea.
You can move here, you can deform it like any.
You can, I mean, you can do quasi-Coulomb deformation, so probably can get any, almost any, I don't know.
Is there something special you're using about twisting by 1/2 specifically, like that it's rational?
It's very symmetric. So, so what I use actually, so when you have very symmetric situation of twist 1/2, then you can cut off your surface in half, and then you look at the curve family going to infinity, and then whatever was in the back, you can using this anti-conformal map, you can flip it in front. And then from one curve family, you can get to the curve family where everything is in front. And then the modulus of one curve family being 0 is equivalent to modulus of the other curve family being 0. So that's the specific thing I use for the 1/2.
So could you do like 1/q and have something for those?
No, I don't know how to do that. Yeah, that was like, yeah. I don't have that kind of symmetry. And then the point is that now when you cut it in half, this is simply connected. So then if you look at the universal cover, and when you just it's simply connected, it lifts simply to the universal cover, and you get this infinite polygon, and then you look at the curve family going to infinity. Well, now the answer is this a single point or an interval? If it's a single point, then modulus of this curve family is 0. If you remember the first example, or one of the first examples, modulus of this family is 0. So that's the proof. Yes.
You know what happens with the examples which are in hyperbolic 3 space, where the group is geometrically finite but has this feature? That is, the limit sets or everything, like these things that fiber over the circle. Is the geodesic flow ergodic there or not?
I don't know. So is the surface is compact, right?
No, the manifold. No, the manifold is not compact. The standard construction by Jorgensen is a Z cover of one of those, and it's still geometrically finite.
Okay.
And so it looks like this one end that you have. And it's known there that, I think Sullivan studied it, but I can't remember if he answered this question.
I don't know, but yeah.
But so I guess I was asking, is it known in every case?
For the Z covers?
Well, I think the Z covers.
Z covers are known, yeah.
And what is it?
If it's if it's Z or Z squared.
It depends on the number of the rank.
If Z cubed, then no.
So it's like Euclidean space.
Yeah. Cool. Yes.
So it seemed from your picture here that your results were a little flexible. What about the like two-ended infinite flute or the
Yeah.
two-ended law?
So anything good works. Actually, these results, when interpreted appropriately, they work for even countable many ends. You can even do transfinite induction on countable many ends, and you can get the same results. This is the only reason why I never thought I'm going to even look at this. The only reason on this surface is because if you have countable many ends, to reach every end, you have to do transfinite induction. You have to cut first you look at the space of ends as topological space, which is countable. Then you cut first you reach the ends which are isolated, and you cut them out. Then you have another class of isolated ends. You cut them out. You do this countable many times. You get the first ordinal. Then you do those ends. You can keep going, and at the end you get empty set, and you say, "I'm done. I win." So
That's each end, but the point is that each end is its own story.
yeah, and you can kind of cut off, and you can see geometrically how this. They're like tree trunks with cut off branches. That's how the neighborhoods look like. Infinite tree trunks with cut off infinitely many branches.
Okay, if there are no questions, let's thank.